Hey everybody, what's up? This is Dr. White back again with some work on the Poisson distributions using R. So you log into RStudio and here I see there's an old file that I'll go ahead and close. I got an empty global environment, which is cool. Let's go ahead and restart R, unload any packages we might have loaded, just so we all start at the same place. And looking in my files pane, let me go to ... and pick up today's materials. So / common folder, Dr. White stuff, Math 331, and it's in scripts this time, section 2.7.r. Okay, so we see we got a lot of things we want to talk about today from the table of contents. Let's get going. So first of all, how do you compute probability mass functions for Poisson random variables in R? Let's set up a situation for ourselves. Actually, let me go ahead and enlarge the screen because you might appreciate that. Okay. Let's say that people who floss regularly get one cavity every 20 years over the course of their life on average. And let's say that cavities as events over time they come like a Poisson process. And let's say that Sarah flosses. Okay, what's the chance that she gets one cavity, exactly one cavity, in the next 10 years? 10 years. So let's let capital X be the number of cavities in 10 years. And let's figure out the distribution of capital X. Well, the rate is a cavity every 20 years, so a 20th of a cavity per year. So 10 years times a 20th of a cavity per year, 10 over 20 is a half. You expect half a cavity a year in this Poisson process. So X actually has Poisson distribution where the rate lambda is 0.5. Well, there's a Poisson family of functions in R, and d Poisson is going to give you the PMF. You just put in the value whose probability you want to know, and you got to tell it what the rate is, and that's done with a parameter called lambda. So let's run this, and we get about a 30% chance that in that 10-year period she's going to experience exactly one cavity. What's the chance that she gets no more than 3 cavities over a 50-year period, over 50 years, okay? Well, then it's the 50 years times 1/20th a cavity per year, and that works out to 2.5 cavities expected in a 50-year period. So if you let X be a new random variable, the number of cavities in 50 years, then X would have a Poisson distribution with a lambda rate of 2.5. Now we want the chance of no more than 3, so we're looking for a cumulative distribution function at 3. So we use the P Poisson, and we stick in 3 and the rate of 2.5, and we get about a 76% chance of getting no more than 3 cavities during that time. Good for Sarah. Okay, next up, let's give ourselves a Bayesian problem. Let's say that 90% of the world's population flosses and 10% of the population does not floss. So 90% are good goobies and 10% are bad people, okay? Let me correct a typo there. And let's say that non-flossers get one cavity every 5 years on average, as opposed to the flossers who are at 1 out of every 20 years on average. And now let's say St. Peter, who guards the pearly gates of heaven, let's say he won't let you through the pearly gates if he suspects that you did not floss when you lived, okay? So imagine George here, who dies at age 80. He's at 80 years of lifespan. So he dies and he reports to St. Peter, up at the pearly gates. And Peter looks in George's mouth and finds 14 cavities. And George says, well, yeah, I've flossed all my life. I just had a bad run of luck. Got a lot of cavities. But really, I was a flosser. And You know, and George has a kind of a case that he can make to St. Peter, because only 10% of the population didn't floss. But St. Peter, he knows those facts about the population, but he doesn't trust anything that people say to him. He only trusts his eyes. He sees the 14 cavities. So he needs to figure out the probability that George flossed, given that he's got 14 cavities. So here is my proposed solution. Over 80 years, a flosser could expect 80 times that 1/20th rate, 4 cavities. But over 80 years, a non-flosser could expect 80 times the 1/5 rate, 1 every 5 years, it says up there. And 80 over 5 is 16 cavities, okay? So let's go ahead and find what's the probability that you get 14 cavities if you flossed all your life. Okay, so that would be a D plus of 14, where the rate is 4 cavities expected over your 80-year life. And we can compute that and get it into our global environment with the name 14 flossed. And you can see over here in the global environment, 5.6 times 10 to the minus 5, that's what that E minus 5 is saying to you. So it's a very small number. We could also just print it out here and see it in the console. Okay, very small probability. On the other hand, what's the probability of getting 14 cavities if you did not floss? So that would be D plus 14, where you expect 16 calories in that 80-year period of time. So we compute that, and we can see that's still kind of a small chance. It's about a 9% chance. Here, I can print it out to the console if you like. So now St. Peter is trying to get the posterior probability that George was a flosser, given that he's got 14. So he uses Bayes' theorem, and he looks at the probability that George was a flosser prior, 0.9, times the probability that a flosser would get 14 over the probability of getting 14 conditioned out, So that's Bayes' theorem. And so we run it, and 0.005 roughly. So that's about 5 out of 1,000. That's about a 1 in 200 chance. So, even though George could plead and plead, hey, 90% of the population is flossers, still, given that he's got the 14 cavities, there's only a 5% chance that he's a flosser in St. Peter's eyes. And so probably St. Peter will turn him away, and George will have to go somewhere else to spend eternity. Sad. Okay, last thing is, let's explore the shape of Poisson distributions with our dist explore function from the BCSCR package. So we'll run this little command, get the app up, and I'm going to do away with my face. And let's go to Poisson. And so you get the facts about Poisson over here. The expected value of Poisson is the lambda. The variance is the lambda as well. And you can choose your lambda. And then you get a probability mass function for the number of events in a unit time with that rate. Right now, the rate is set at 3 events per unit time. You can vary that if you like. And here's an interesting thing I find. If you start off with a really low rate, you get a very right skewed distribution. But if you just increase the rate, up to 2.7 now up to 8.4 events per unit time, now up to about 15 events per unit time, now up about 25 events per unit time. Look at the shape of the distribution. It's less and less of a right skewed distribution and more of a symmetric bell shape. This is like, I don't know, the third time we've seen this kind of thing. Binomials, when you bump up the number of trials, get looking more and more bell shape in their PMF. Negative binomials, if you bumped up the number of successes you're waiting for, you could get them to look more bell-shaped too. And now we're seeing it with Poisson. If you bump up the rate, then you're getting more and more bell-shaped. There's something interesting afoot here that we really would like to dig into as we develop more powerful probability theory, see if we can understand what's going on there. Anyway, let's close the app. And so we have to push the little stop sign at our console to really get it to stop listening at that port and listen to future commands from us. And I'm going to go ahead and clean out my global environment. And I'll just get my files pane to be looking back home. And then I'll log out. And I'll see you later.